Welcome everybody to lecture 11. This is a continuation of what we did in the last lecture, namely obtain a rather meaningful and important relation between the relativistic mass of a particle and its energy carried. The essence of what we found is there in equation 116 in lecture 11, which is page 58. From this we know that the kinetic energy is the rest mass energy part deducted or subtracted from the total energy, leading to half mv squared in the lowest order approximation and with increasingly higher order terms as you stop neglecting powers of v over c. Given this, we have already learned that putting a particle or making a particle more energetic essentially means pumping more energy, which is the condensed energy lump called mass, increased with a portion of the mass depending on the velocity, manifesting itself as kinetic energy. In any case, in any inertial frame, it is therefore quite automatic that we define the momentum as the relativistic mass times velocity, equation 118. There is a typographic error. P is not equal to m naught v. It is mv equal to m naught v over square root of v squared by 1 minus v squared by c squared. So knowing equation 118, which is following in a very straightforward manner from the results of the previous lecture, you square both sides, do a little bit of algebra, very simple algebra, and arrive at equation 119, which tells you the total energy squared is momentum squared c squared plus rest mass squared times c to the power 4. The total energy, you should remember, includes rest plus kinetic energy. This is its contrast to the usual practice where momentum is P, total kinetic energy is P squared over 2m, and that's all we talk about in terms of energy, simply because the rest mass energy is a content which is sort of a dead weight staying with the rest mass, and it influences dynamics only through the mass itself. So it is not separately spoken about as energy or adding to the content of energy. In a relativistic situation where mass varies, acquiescence or release of energy leads to an enhancement or a fall in relativistic mass. So having this relationship, E squared equals P squared C squared plus M naught square C4, it is straightforward to use the expression for E to obtain the velocity of a relativistic particle in terms of its rest mass, its total energy, and of course, velocity of light c. There's an exercise after this, which I request you to work out. These are all homework assignments in the last lecture as well as this one, because these are bordered with blue lines with two double lines at the left. Before we leave today's discussion, just a couple of points to touch. First is, of course, reminding ourselves that rest mass, if there is a scattering of two particles to two particles or one particle breaking up into two particles like we considered in the previous lecture, rest mass is not necessarily conserved. What is conserved is total energy. Rest mass conservation came as a kind of automatic assumption in non-relativistic thing because we were considering energy only in the form of kinetic energy. When that is not the situation, rest mass can change. So this is the principle underlying the nuclear bomb, as we have already said. And this disappearance of a little bit of rest mass to release some energy can manifest itself in a huge amount of energy produced through the disappearance of a rather tiny amount of mass. Of course, 1 gram is a large number in this respect, but you can see 1 gram of radioactive material nuclear mass lost in a set of reactions from a lump of nuclear uh, fuel will lead to a huge amount of energy, which supply 3 megawatts of power for 1 year to an operating electrical system. Also, when it comes to a photon, you should remember photon has no rest mass. It is moving with velocity c, so it has no rest mass. Otherwise, the equation for relativistic mass will be inconsistent. So P equals m times c. E is, of course, m times c square. That gives a very straightforward relationship between the total energy of a photon and its momentum. Of course, the mass is relativistic mass. Only by virtue of its motion with speed c, it acquires a mass. The rest mass is zero. And of course, here the energy is E equal to h nu, as was hypothesized by Max Planck in 1900, when black body radiation spectrum could not be explained from more fundamental properties of electromagnetic radiation. Planck finally had to go back to the hypothesis that actually absorption or emission of electromagnetic radiation occurs in packets, each of which contains energy h nu, when nu is the new frequency. Later on, Einstein placed this hypothesis on more solid grounds by explaining photoelectric effects in terms of these particles exactly behaving like uh, particles or corpuscles of light, and these were given the name photon. What we have said just now concerns the energy and momentum and their expressions of such photons. And I end with an exercise, which is an assignment for you about the relativistic mass of a yellow light photon. Just work it out and they will be more convinced of the whole thing. So we end this lecture here. Thank you for your attention.